In this video, we're going to look at velocity time graphs and two different situations. In the first, we'll have a train, and in the second, we're going to have a particle that begins with an acceleration only and no velocity. And then we're going to draw velocity time graphs of them and look at some features of the motion. So let's start now. We've got two train stations. They're 3.5 kilometers apart, so we can imagine them just in a straight line. A train starts from rest, all right, at A, is uniformly accelerated to its maximum speed, some maximum speed that we wish to find, travels for 1 kilometer at this speed, whatever that is, and then is uniformly retarded or decelerated to come to rest at train station B. Now, if the whole journey takes 5 minutes, find the maximum speed. So this is where a velocity time graph comes into its own. What we're going to do is let v meters per second be the maximum speed and t seconds be the time for which the train travels at this speed. And this is capital T. Okay, so this is the middle part of the journey where it travels at this maximum speed v, whatever that is, and it does it for capital T seconds, all right? And it travels for 1 kilometer at this speed. Okay, so we expect a velocity time graph to look like this. Time across the horizontal axis. We don't expect time to have a negative part there. Shouldn't draw that in. Best if you don't draw that in at all. Okay, up the side here, velocity. Now we're going to start from rest. It's going to accelerate up to some maximum speed, and velocity. It is velocity because it's all motion in a single direction, but we can say speed because we're really only interested in the magnitude, and same with distance. There's no negative velocities here, so we don't have to worry about areas below the axis here with their negative values. Okay, it's all positive value here. So for us, the displacement from train station A to B will be the same as the distance traveled. Okay, remember there is a difference between displacement and distance. If I walk a circle, I begin and end my journey at the same point on the circle, then my displacement is 0, but my distance traveled will be the circumference of the circle. So in that case, where direction is involved, they are two different things. But if you're traveling a one single straight line, then your displacement will be the same as your distance traveled. All right, notwithstanding direction, of course. So our train takes off from station A, uniformly accelerates to a maximum speed. It travels at maximum speed and it completes a distance of 1,000 meters before it starts uniformly decelerating down to 0. The total length of time here is 300 seconds. It's 5 times 60 seconds. 5 minutes is 300 seconds. Okay, we know the area here for this rectangle CDEF, we know that to be 1,000 meters. Okay, we're given that it traveled 1 kilometer at this constant speed. Okay, that gives us our first bit of information. Okay, other than the area of the trapezium itself. Now, the trapezium itself, the total distance between the two stations is 3.5 kilometers or 3,500 meters, and that will be equal to the area of the trapezium ACDB. So it's the area under this velocity time graph. The area of this trapezium will be 3,500 meters squared. Okay, the distance traveled at constant speed will be 1 kilometer or 1,000 meters, and so the area of this rectangle CDFE will be 1,000 meters squared, which means that we can write for this rectangle, we can write the relation. The area of this rectangle has got to be equal to the base length, which is capital T units in time, so capital T units in time, and our height, which is V, capital V. So capital V times T is equal to 1,000. That gives us the area, okay? Base times height. Now, area of a trapezium. Let's just remind ourselves what that is. Let's just go down here to the right. Here's a trapezium. This length's A, this length's B. This is the vertical height. Then the area is the two lengths A and B added together in parentheses times the vertical height divided by 2. Okay, so in relation to our trapezium now, the train journey, area of this trapezium will be this length here, which represents capital T units, plus this length here represents 300 seconds. Okay, so there's our two distances here. Our vertical height is capital V here, and we divide by 2, or multiply by half. Okay, that's the area of the whole trapezium. We also know the area of the rectangle in the middle. V times T is 1,000. Okay, well, next step, if we want to find our maximum speed, is let's take our expression for the area of the trapezium, a half times T plus 300 times V is equal to 3,500. Let's multiply through by V on 2. So we have a half V times T, and a half times 300 times V is equal to 3,500. Okay, we can replace V times T with 1,000. We've already found that. That was this relation here. Okay, so half times 1,000 plus a half times 300 is 150 times V is equal to 3,500. Okay, half of 1,000 is 500 plus 150 V is 3,500. Subtract 500 from both sides. 150 times V is equal to 3,000, and so V gives us 20 meters per second. So our maximum speed is 20 meters per second, and that's what we set out to find. Okay, so there's a use of areas under velocity time graphs. Okay, let's have a look at a different type of question now. And what we've got here is a particle traveling in a straight line. Okay, so again, we're just dealing with straight line motion. It begins with an acceleration. That's what sets the whole thing off. Doesn't have any initial velocity. Okay, even though the problem doesn't say that, it just begins with an acceleration. So it can be at rest. It might be that I've got a slingshot and I'm going to fire this slingshot. I pull back the rubber with the little stone inside, the little particle, and the instant I release it, it has zero velocity at that instant, but it has a massive acceleration acting on it. Okay, now this acceleration decreases uniformly from 30 meters per second to 0 in 15 seconds. So our acceleration is going to go from 30 meters per second to 0 in 15 seconds. It then continues to move at a constant speed for 5 seconds, okay, a bit like the train above, and finally travels with a retardation or deceleration of 25 meters per second until it comes to rest. It's all motion in one direction. There's no reverse velocities. We won't have any negative velocities or anything. Our graph will be strictly in the positive direction of the velocity axis. There won't be anything below the axis. The particle moves in one direction until it comes to rest. We want to draw a velocity graph and find the distance traveled. Okay, so here's our particle. How far has it gone, given all this information? All right, we need to find out a little bit more about an expression for acceleration, because acceleration is related to the rate of change of velocity. And a velocity time graph is what we're hoping to achieve. So A goes from 30 meters per second to 0 in a time of t equals 15 seconds. So let's try writing A equals 30 minus some constant times time. It needs to be time related because it has to happen over 15 seconds, and it decreases uniformly. So it rather suggests a linear type relation. Well, now A is also equal to the rate of change of the speed with respect to time. Okay, rate of change of speed with respect to time. So if we write that to be 30 minus kt, we know that the acceleration is 0 at the end of the 15 seconds. So 30 minus 15k has got to be equal 0. While solving that, k must be 2, so we put 2 in there. Okay, so we now have a derivative, a function which describes the rate of change of the speed with respect to time, dv dt, and that's 30 minus 2t. We're interested in the velocity though, because we want velocity versus time. But from that first order derivative there, we can have dv dt as 30 minus 2t. We can anti-differentiate that to get v. So let's anti-differentiate that. dv dt with, integrated with respect to dt, okay, with respect to t, time, is equal to the integral of 30 minus 2t integrated with respect to t. Okay, and that will give us, anti-differentiating that, 30t minus t squared plus some constant of integration. We need to find that constant of integration because we need a particular solution, because we're dealing with a real-world physical problem and we want to describe that. We don't want a whole class of curves as our answer. So we need a constant. What is it? Okay, now v equals 0 when t equals 0, because remember we started with just net acceleration and no velocity. Its motion begins. I know it's not obvious in the question. It can be a bit difficult, this question, but it begins with an acceleration. So v equals 0 when t equals 0. Now, if we substitute t equals 0 in here, we're just left with c, and we know that v equals 0, so c must equal 0. And so our velocity speed function now, or velocity function, becomes 30 times t minus t squared. Okay. And when t equals 15, all right, when t equals 15, when v equals 30 times 15 minus 15 squared, 450 minus 225, and that will give us 225 meters per second. Okay, so after the 15 seconds, the acceleration has gone to 0 and it's now moving with its maximum speed, which is 225 meters per second. So we can start to build a graph now. Okay, we have velocity, time. Okay, velocity is initially 0, but this tremendous acceleration is acting, which decreases, which is why we have a curve, because if you look at the curve, it's 30t minus t squared. It's a concave down parabola, okay, inverted because of the minus in front of the t squared. So it's concave down, and it does that for 15 seconds. It then travels at a constant speed, okay, for, what was it, 5 seconds again, was it? Yeah, 5 seconds, and then finally acts with a retardation of 25 meters per second until it comes to rest. Okay, so we've got this, so from 15 seconds to 20 seconds, we can just draw a horizontal line at 225 meters per second. But what we need to do now is from the 20-second mark, it's going to drop down to 0, because there's going to be a deceleration acting, minus 25 meters per second in the opposite direction to its motion in order to bring it to rest. We need to find how long that takes. How did I get 29 here on the sketch? Okay, well, we can use the equation. We know that u is plus 225 meters per second. V is 0, the final velocity is 0, so the initial velocity is 225 meters per second, final velocity is 0. The acceleration is, or deceleration is, minus 25 meters per second. We must put minus there. What is t? Well, we can use the equation v equals u plus at. We can transpose that to make t the subject. And when we do substitute in the values that we know, we have 0 minus 225 on minus 25. Okay, the negatives cancel. 225 divided by 25 gives us 9 seconds. So it goes from a speed of 225 meters per second to 0 in 9 seconds. So our sketch must go all the way up to 29-second mark. Okay. We naturally divide now the sketch into 3 sections. We have this first area here, we have a second area here, and we have a third area here. Okay. Area 2 is straightforward. It's just the base times the height, isn't it? So it's going to be 5 times 225 to give us 1,125 meters. Okay, area 3 similarly is just a triangle, a half the base times the height, so a half times the base of 9 times the height 225. That gives us 1,012.5 meters. Okay, now for area 1, to find the distance travelled there, we need to look at the integral of the velocity function. Okay, and we need to anti-differentiate that, which gives us the position function. So v is dx dt is 30t minus t squared, okay, which is sketched here, 30 minus t squared. We need to find the area under this curve, and that will give us our distance travelled or displacement, since they're both in the same direction. So the integral from 0 to 15, the definite integral from 0 to 15 of 30t minus t squared, integrated with respect to t, okay, will give us, this is 30t squared on 2, which is 15t squared, minus t cubed on 15, evaluated between 0 and 15, okay, gives us, well, evaluated at 0, this will disappear, so it's just the first part we need, which is the top terminal here, 15, so 15 times 15 squared minus 15 cubed on 3. Well, that's 15 cubed minus 1/3 of 15 cubed, so it's 2/3 of 15 cubed. And when we evaluate it on the calculator, we'll find 2,250 meters. Okay, so we now have area 1, area 2, area 3, and so the total distance traveled, or displacement in this case, will be 1,125 meters plus 1,012.5 meters plus 2,250 meters. Added together gives us a total distance traveled of 4,387.5 meters. Okay, that's it.